Hello, and welcome back to California Geology. I am Dr. Robert Lopez, and today I want to talk about transform margins and divergent margins. In a transform plate tectonic margin, we have shear stress, where two tectonic plates or two blocks are sliding side by side each other. And what results are these strike-slip faults, right? A strike-slip fault is where the movement is in the strike direction, as we discussed already. Remember, strike is a compass direction. In this case, I'm add in reference to north. So usually, for example, on this one, let's say we had a north arrow indicating the north direction. Since this fault is trending slightly to the west of north, we would say that it would have a northwest strike, a northwest strike. So that's the direction, right? The horizontal direction. Strike-slip faults or transform plate boundaries show offset, right? Offset. And offset is basically you're taking something and you're gonna break it in two. Move one in one direction and move the other side in the opposite direction, right? So in this case here, we're seeing the offset of this creek. I have a little stream coming down here, and you see that this side here on the west is moving north, whereas the side on the east is moving south. And the way we differentiate the sense of offset, or really the sense of movement, is by using these words either right lateral or left lateral strike slip. For example, right lateral, we can use the word right stepping. Left lateral, we can use the word left stepping. Older terms we used to use was dextral slip for the right lateral slip, and sinestral slip for the left lateral strike slip. So going back to my model, let's see what type of motion or offset this fault is here. So if you were standing here on this creek and you're looking or walking up the valley, you'd run into the fault, and you would have to step to your right to get back to the creek, right? So that's a right stepping or right lateral fault. By the same idea, if you're coming from the east down the stream valley here, you would get to the fault, right? You're facing the fault, and you would have to step to the right to get down to the valley again, right? So no matter which way you approach the fault, whether you're coming from the east, you step to the right, or you're coming from the west, you step to the right. So this is an example of a right lateral strike-slip fault. Most transform boundaries are going to be in the marine or oceanic setting. My little cartoon here is of a mid-oceanic ridge. These double lines represent a mid-oceanic ridge where there's tensional stress or divergence going on. And then this tectonic plate over here, we'll call it plate A, is moving toward the west or the east, whereas plate B over here on this side is moving toward the west. So there's seafloor spreading going on here, right? We're generating new seafloor. Now, between the offset ridges here, right? Since this plate A is moving to the west, we're going to draw a half arrow showing that direction, and plate A is moving toward the east. We'll show another half arrow. There we have a transform strike-slip fault. And if we think about the sense of motion, if we were stepping across the fault here, we'd have to step to the left. So this is an example of a left lateral strike-slip fault, right? So an object here, you would find it over here. It'd be offset to the left, right? And then other things that we can point out here, note that these stippled lines that I've drawn here, they occur within one tectonic plate, right? These are called fracture zones, a fracture zone. And note that there are no earthquakes on fracture zones. So the plate tectonic boundary is really at the mid-oceanic ridge and at the transform. That's the only place where plate B and plate A are in contact, right? So these other lines here would be fracture zones. Going back over here to our PowerPoint, here's another diagram showing the same idea, right? Here is a mid-oceanic ridge, the transform fault, right? And you can see the offset here. In this case, again, we're looking at a left lateral strike-slip fault, right? What I have here in your text, I have or in the PowerPoint, I have the San Andreas Fault. You can see it's a very linear fault here, and this is a place over just south of San Juan Bautista, near Hollister. It's called the De Rosa Winery today, but it used to be called the Cienega Winery. And the San Andreas Fault goes right along here. And this culvert was built in the late 50s, and you can see the culvert is offset. So if you're walking up the culvert here, you would have to step to the right to get back into the culvert. And so again, the San Andreas Fault is an example of a right lateral strike-slip fault. I also have this map of Southern California showing the San Andreas Fault here, right? So if you look at the San Andreas Fault proper, there's a lot of rocks over here in the Chocolate Mountains, up here near Joshua Tree, near the Colorado River corridor here. And these rocks are sediment rocks and conglomerates and gravels that were shed off these mountains onto towards the west here. But movement on the San Andreas Fault has moved the rocks that were here and has carried them far to the north here. And here they are, right? In fact, they're called the Mint Canyon Formation and the Caliente Formations up here in the LA basin area. And these were once down here, right? So if you were standing at the Mint Canyon Formation and hit the San Andreas Fault, you would have to step far to your right to get to the Chocolate Mountains and Joshua Tree, right? So again, an example of a right lateral strike-slip fault. On the other hand, the Garlock Fault over here in the Mojave Desert, so this is the Mojave Desert region here. This Garlock Fault, there are rocks here of the Ricardo group in Red Rock Canyon off of Highway 14, and if you see that if you go across this Garlock Fault, they disappear and you find them far to the east over here, right? So if you're in these same rocks here and you hit the Garlock Fault, you would have to step to your left, right? You would turn yourself around here, face the fault, and step to your left. So the Garlock Fault is an example of a left lateral strike-slip fault. All right, now let's look at divergent margins, right? So a divergent margin involves tensional stress, and the lithosphere will be thinning because you're pulling apart, right? You're pulling it apart, and these divergent margins are common to mid-oceanic ridges. And what's happening at these mid-oceanic ridges, there's going to be seafloor spreading, where the seafloor spreads apart and magma will come up from beneath, right? So we're going to see magma and volcanoes at these mid-oceanic ridges that come up through the thinning lithosphere there, right? Now this process is called seafloor spreading. And seafloor spreading is a process of generating new seafloor at the ridge axis that then moves directly away from the ridge. Seafloor spreading. We're creating new seafloor and then it's moving away from that ridge to form even newer seafloor, right? Those are correct divergent margins. There's two divergent margins or mid-oceanic ridges I want you to know about. The one in the Atlantic Ocean has a rate of about 2 to 3 centimeters per year. That's about how fast your fingernails are growing. And most tectonic plates are moving at about that speed, about an inch per year. Remember, 2.54 inches 2.54 centimeters in 1 inch. Now, for the Pacific plate, or we have this East Pacific Rise, right? The East Pacific Rise. And this is the mid-oceanic ridge in the Pacific Ocean Basin. And it's moving quite a bit faster, 10 to 16 centimeters per year. And you can see right away, because this ridge is moving so fast, remember the basin margin around it, we have the ring of fire, right? So the ring of fire is partly due to this fast spreading at the East Pacific Rise, right? And also at these mid-oceanic ridges, we're seeing volcanoes, right? And volcanoes are erupting lava onto the seafloor. And I have a little video here that I want to show you of this basalt lava pouring onto the seafloor. And when it hits that cold seawater, that hot magma quenches into these pillow structures. And we call these pillow basalt lava.
Submarine flows form pillow lava, as cold seawater chills the magma to produce a brittle crust, which cracks open, allowing the still molten interior to flow out and repeat the process as new crust forms on the freshly exposed lava.
So that little video describes what's happening. This is figure 1-5 from your textbook, right? As the lithosphere thins, magma comes up from the asthenosphere, a process called decompression melting. We'll talk about that later. And that erupts at the mid-oceanic ridges, and that lava pours onto the seafloor. The key thing, the seafloor is covered by pillow basalt lava. Covered by pillow basalt lava. And then it breaks in two and moves directly away from the ridge, right? Here I have the peridotite mantle and the crust up here. So that line right there is a separation between crust and mantle. And you should remember that line is called the moho. Well, let's stop here and we'll continue later on.